Okay, I'd like to solve a next example here using like Gauss law to calculate the electric field, and I'm going to use this law to calculate a problem that has a planar symmetry. So I'm going to consider an infinite plane with a uniform surface charge density sigma, and like I said before, I'm going to find an expression for the electric field strength uh, at a point P located above, doesn't matter, but above, not on the plane, but above or below the plane. So this is the symmetry I'm going to use. Here is the plane. Here is the electrical, sorry, the charge surface charge density, and I'm going to use this reference frame to solve this problem. The first step here is to identify the symmetry, and since this is a plane, it's convenient to put like the xy axis like on the plane, and put and place the the z axis on the perpendicular to this plane. So that means that I'm going to have symmetry in the in the z direction. In this sense, guys, so this was the first thing that I have to do. I have to spend some minutes to actually to identify the symmetry. I'm going to put this here because this is important, the first important step, and this is going to save a lot of time calculating. So we have to I and the next step is actually after, of course, after you identify the symmetry, the next step is to select, choose Gaussian surface, and now I chose since we have symmetry in the z-axis, doesn't matter if I choose like a box, or I could choose like a cylinder too, like this. uh, Input here would be, the results would be the same. In this, for this example, I'm going to use like a box, and the Gaussian surface is going to be a box, and since our electrical field, the electric field for and I'm going to have exactly the same in the opposite direction. Direction. Right there. Okay, so the normal vector, this problem is going to be right here. I'm going to make very big, so I'm not going to, because it's going to be kind of tough. It's going to be very polluted. So maybe top and the bottom surfaces here. Our vector, like unit vector, is going to be K. Minus, and okay, so this is it. This is the top surface. This is the only one I have to take care actually. This one up. So the third step here is actually to calculate the electric flux for this particular problem using this symmetry. Mhm. Going to be, of course, all a closed surface integral. I'm going to separate, so we are going to have one contribution for the lateral surfaces. We are going to have the two, they're going to be exactly the same, since when you calculate the scalar product, this and this is that for the top and for the bottom surface going to be the same. So that means we're going to have here twice integral here. a hat, and this is going to be easy. This one is going to be 1, and these two, since the normal vector here, normal vectors for the x and y directions are going to be perpendicular, the electric field. So this has as a consequence that this scalar product is going to be 0. Integral, we don't need to calculate since this everything is going to write here just as a reminder of how to solve this. Okay, so we're going to have only this result here. This is going to give me E in the area of this square is going to be, so electric flux is going to be twice E electric field multiply the area top or bottom surface this box. One. So the fourth is, we're almost there, so just a little more, couple more steps here. So the fourth step here is to determine the enclosed surface, the enclosed charge. Have to determine that, and this is very easy since we have the surface charge density. We know that the surface charge density just the ratio between the charge and the area. So that means we can write actually the enclosed charge as the sigma times and finally the fifth step is actually evaluate, well, determine, to find to an expression for the electrical field, for the electric field. And for that is very easy. I just have to substitute the equations 1 and 2 in Gauss law. So you can find this. We know that actually the electric flux will enclosed charge divided by the free space, permittivity of the free space. So this is then just have to substitute one and this one. This is going to give me 2 equals to sigma a, everything divided by the epsilon 0, epsilon 0. So the two areas cancel out, and this finally gives me one expression for the electric field for the infinite plane going to be sigma over 2a. And what is the significance of that? Well, this is the same expression that we calculated, that we found using the problem of the charged disk. Exactly the same. As you can see, this way was way easier than what you did before. You can recall, if you can remember, this like a lot of time and effort find this expression. Let me put here everything. Let's go back, try to find some that I just mentioned. Here this took a look. This gave us a lot of trouble. Have to restart having this one, electrical field for a ring, and you derive like an for the charger disk. That was very complicated of work. But here no, actually what was it is way easier using Gauss law. That's all. That's all I wanna explain today. So much for your attention, and like always, acta est fabula.